All right, so at last, we're ready for series in calculus. Now, you've seen series before in Algebra 1, not Algebra 1, Algebra 2 probably, in pre-calculus, college algebra, that kind of thing. But previously, they were mostly about sequences, and they were all either arithmetic or geometric. So we either get the next term by adding something to it or by multiplying by something. In calculus, you'll never see arithmetic, you'll only see geometric, but most of the terms, most of your series won't even be geometric. They're almost always going to be some weird hybrid, and that's part of why we're going to learn crazy things like what a P-series is, or a power series, or a Taylor series, is because nothing's going to be a geometric anymore. That's like too easy, and it's too easy just to apply stuff you know from Algebra 2 to it. So every once in a while, a geometric series will pop up, and we'll use some of those rules that you actually learned back in Algebra 2. So keep your eye out for geometric series, but you'll almost never see one. It's almost like a trick question when it turns out to be so easy. It's like, oh, it's a geometric series. Why didn't I think of that? You know, that's like the trick. Those are the easy ones. The things that seemed hard back then are now going to be the easy ones, and the hard ones are going to be, pretty hard. But this chapter is going to be all about learning the rules to figure out if a series is converging or diverging. Don't worry if you don't know what that means yet. We're about to go over it. All the following videos will be about the various tests for convergence and divergence, the comparison test, the limit comparison test, the ratio test, all those videos you see below this one. As far as Taylor series and Maclaurin series and power series, those are going to be in following chapters. This chapter is just about all the different tests for convergence and stuff. And just as a reminder, looking at this thing you haven't seen in a while possibly, this is sigma notation because this giant weird looking letter is a capital sigma, whatever that means in Greek. Might be an S. Not sure. I think the lowercase one looks like this. But either way, the point is, what this means is that we're going to start at 1, or if it had said 0, we start at 0. And we go to infinity. In calculus, we're almost always looking at infinite series, so there'll always be infinity at the top. And then this is saying, hey, add up all the terms. So we're going to plug in 1 to this. Then we're going to plug in 2. Then we'll plug in 3. So for example, the first term, we plug in 1. Factorial is just 1. 1 minus 1 is 0. So the first term is 0. And then because it's a sigma, that means we do a plus sign. And then for the second term, we'll plug in 2 for n. 2 factorial is 2. 2 minus 1, so we get 2. And that's just how it goes. We go from 1 to infinity. Obviously, we'll only do a few terms, then we'll put a plus and a dot, dot, dot. But the point is, that's what sigma notation is. This is what you're going to see in calculus. You'll almost never see sequences. So just as a reminder, what a sequence is, it's when you have a series of numbers with commas in between them. So they're just sort of each term stands on their own. In calculus, it's going to be always going to have the plus signs in between the numbers. And they're almost always going to end in a dot, dot, dot because they're infinite. All right, convergence versus divergence. This is the big concept of this chapter and what they're going to teach you a lot of different methods for and tell you some theorems. But what you're ultimately trying to figure out is, does a series converge or does a series diverge? And because we're talking about infinite series, you can kind of see how it's easy for something to add up to infinity. If I go to the next slide real quick, you can see how this series right here, where we just add up all the integers, that's going to get big in a hurry, right? Because by the time we get to 1,000, we're adding 1,000. So if you actually start adding up these numbers, it's obviously going towards infinity really fast. The total sum of this series is going to be a ridiculous number, and it's basically infinity. Or you could say it diverges, because remember in limits, how often instead of, if the limit was infinity, instead you would say the limit does not exist, or the limit diverges, is how some teachers say it. Well, in series, if something adds up to infinity, then pretty much everyone says the limit or the series diverges. And that's true of this one too, obviously, only it gets bigger even faster. And even if you had just one number added again and again and again, if you add 1 to something infinity times, it's obviously going to add up to infinity. So these are a bunch that diverge because they add up to infinity. And you might be thinking, hey, how could I have infinite terms not add up to infinity? Because if I add infinity things together, aren't they always going to add up to infinity? Well, it turns out that if the terms get smaller as they get, as you work your way along the string, if the terms get smaller and smaller, it's possible for them to add up. Oops, go back to the previous slide. It's possible for them to add up to a finite number. So let's do these second two first because they're more obvious. If you add 0.1 to 0.01 to 0.001, you're actually going to get just a repeating decimal, a million ones in a row, or you might just write it 0.1 repeating. whatever. But the point is that each one of these terms just adds one more 1 to the decimal. And if you convert this to a fraction, that would actually be 1/9. So infinity terms adding up to a small fraction like 1/9. Pretty impressive stuff. And this was a relatively simple one, but it's going to turn out that even with more complicated formulas, you could still have sort of the same effect happen to where as the terms get bigger, meaning as n gets higher, like your 10th term, 100th term, 1000th term, if each little term gets itty bitty, then they're just not doing much to the total sum that everything adds up to. And that's how you have a finite sum. This is very similar, but the decimal we're going to get is 0.25, and then 25, and then 25, which is 25 repeating. 0.25 repeating, sorry. Not sure what that adds up to fraction-wise, but the point is it's around a quarter, a little bit more than a quarter. And this one, we'll go back to this. This is a classic that I just want to bring your attention to because you'll see it frequently as sort of an example of kind of a fun series that adds up to an easy number, which is 2. So if we look at the number line, after the first term, we've already gotten to 1. So if here's the number line, there's 1, start at 0. So after one term, we're already at 1. After the second term, we're at 1.5. And here's 2. Add a quarter to that, and we get to right here. Add an eighth to that, we get to right there. And with each successive term of this thing, because these are all just powers of 1/2, with each successive term, we get halfway closer to the number 2. So it turns out that even if you added a lot of terms to this, you'll just keep getting closer and closer to 2, but you'll never actually get to 2. Even if you do all infinity terms of this infinite sequence, you'll never quite get to 2. But just like with a limit, just because something doesn't actually get to that number, we're still going to say the limit is that number. So the sum is never going to actually reach 2, because it'll always just be getting closer and closer to 2 without ever getting to 2. But we're still going to say that the sum of this thing is 2, because that's the number that's getting really, really, really close to. So those are all sequences that converge because they add up to a finite number. And in this class, we're not usually going to find out what the actual sum is, because that can be really hard to figure out. But, or at least in this chapter, you won't. Taylor series and power series are more about finding out what the actual sum is. But in the case of these convergence and divergence tests, we're just trying to find out, is there a number that this thing's approaching? And we won't actually find out what that number is. But we just want to find out if it converges, it's adding up to a finite number. If it diverges, it's shooting off to infinity. All right, so the number one thing to look for with something that might converge is the terms have to get smaller. They have to get smaller and smaller as n gets bigger and bigger. So here's term number 1, 2. So this would be, you might call this a sub 1, a sub 2, a sub 3. And those particular series, you can see that they're getting smaller. 1/2, 1/3 is smaller than 1/2, 1/4 is smaller than 1/3. The formula for this series is 1 to infinity of 1 over n. And that's called the harmonic series. And it turns out the harmonic series, I don't know why it's called harmonic, by the way. Like, what does a harmonica or the word harmonic have to do with the denominators getting 1 bigger? No clue. But this is a very famous series. You're going to see it referred to all the time. And it's interesting because it diverges. So you would think that it might approach a finite number, kind of like this one did, with the powers of 2 downstairs approaching 2. But this one diverges in sort of the classic diverging sequence, whereas this one converges. That's why it can be hard to figure out just from looking at something whether it converges or diverges. So that's why we're going to learn all these tests to figure it out. All right, I'm emphasizing this again. The harmonic series diverges. It's your poster child for something that looks like it might converge, but actually diverges, adds up to infinity. We'll prove this later. We'll actually look at this with several of the videos coming up, like the integral test, the ratio test. There's a lot of tests we can use to show that this is true and it does diverge. I don't know if anything will satisfy your curiosity other than trying to set up a formula on a spreadsheet or your calculator and just adding it up and seeing, oh wow, that thing really gets big fast. But Basically no matter what number you pick, like 1,000 or 10,000, it'll take millions and millions of terms, but eventually this thing crosses any number you can set out for it. All right, there's something else I want to bring your attention to. A video late in this chapter is going to be alternating series. They're called alternating because they switch from plus to minus with each term. So here you can see we're going minus, plus, minus, plus. Kind of silly. The way you get that in your terms, in your formula, it's sum from 1 to infinity. If you have negative 1 to the n over n, let's say, because this thing really looks like the harmonic series, 1/2, 1/3, 1/4, 1/5, but we have these alternating signs. The way you get the alternating signs is you put negative 1 to the n power. Now whenever n is an even power, you'll get a positive 1, but then if n's odd, you'll get a negative 1. And if that ends up not working out, all you do is you throw a minus 1 on there, and all of a sudden that'll make the even terms negative and the odd terms positive. It gets confusing. But the point is, if you want to switch negative, positive, that's an alternating series, and you get that by raising negative 1 to the power n. And kind of interestingly, these things always converge. So if you have a sequence, and we'll go over this in the video about alternating series, but if you have a series where the terms are getting smaller and smaller, doesn't matter what those terms are, it's going to converge as long as it's alternating. So this one right here is the alternating harmonic series, because it's the harmonic series, but it alternates plus minus, and this one converges. I'm not actually sure what it converges to off the top of my head, but it does converge. It's kind of famous for that. However, even if something's alternating and the terms don't get smaller, like this one right here, it diverges. It does not converge. You can kind of see that if we just keep a running total, after the first term, our sum is 1. After the second term, it's 1 minus 1, which is 0. Add another term, we get a 1. So you can see this thing's going to keep on flip-flopping between 0 and 1, 0 and 1, 0 and 1. And just like if you're trying to take the limit of something, if something is switching back and forth forever, then it's not really converging because it's not getting smaller. So there's no value it's approaching. All right, so what if the terms get smaller and smaller? It's not alternating and it's not the harmonic. Like it's one of these funky formulas on the left. Here we got some factorials. Here we got 1/2 raised to a power. That's actually the one we've looked at a bit now. What about this crazy guy? When they give you a random formula that's not one of the famous ones, that's when you've got to use all these crazy tests that we're going to go over in the many videos to come in this chapter. So the integral test, p-series, comparison, nth root, you name it, we're going to hit it. Most calculus classes cover a bunch of these. Some of them don't come up as often, like the nth root test. Very short video because there's like 2 problems you would ever do with it. But that's the stuff to look forward to, so stick around.